In today's lesson, we are going to focus on conceptual density notes. In today's set of notes, we are going to focus on the conceptual portion of density and what density is. So, one real-life example you may have seen of density is if you've ever looked into a cooler on a hot summer day, you might notice that your Diet Cokes will sometimes float at the top and regular Cokes will sink to the bottom. Well, the reason for that is your Diet Coke doesn't contain any sugar, whereas your regular Coke contains a lot of sugar. So when you add sugar into water, the water becomes a lot more dense. Its volume doesn't change, but its mass goes way up. And so that causes your Coke to have all of this like syrups and everything in there that are a lot more dense. Because the regular Coke is more dense than water, that Coke sinks to the bottom. The Diet Coke, on the other hand, since it doesn't have those sugars, it actually ends up being less dense inside of this can, and therefore it floats at the top of the water. Another good example of density, or a good way to explain it, is how much stuff is in a certain space. So a lot of us have seen a picture like this in one of our geography courses, where this is a population density. So these locations where it's really dark red, like if you think of New York, oh, that's off a little bit. So if you think of like New York, Europe, or especially over in like India, or just anywhere in kind of this Asian region, they have a very, very high population density. What that means is there is a lot of people in a certain area. And if you compare that to other places, like Greenland or Canada, Alaska, anywhere up further north, there's not very many people living there for how much space there is. So that is said to have a low population density. Now, one common misconception students have, and this is something a lot of students think, is that density and weight are the same thing. Students will also think that density and volume are the same thing. Just because something has a really big volume does not mean that it's dense. Just like because something has a very heavy weight does not mean that the object is incredibly dense. And I will give you some examples showing this as we go through the notes. So if I were to ask you which object weighs more, a bucket full of water or a gold ring? Well, hopefully you would say the bucket full of water. It has a lot more weight to it. However, if I were to ask you a different question, and I asked you which object is more dense, well, the gold ring, if I were to take that and I threw it into the bucket, the gold ring is going to sink to the bottom because the gold ring is more dense. One way that I can draw this, and I know we're using a little bit of knowledge we don't quite have yet, is if we look at the bucket of water and we start to draw the atoms in there. Really what density comes down to, and you can think of this like population density, think of the atoms as being like people, is in the bucket of water, those atoms are more spread out. So they're not quite as dense. However, this bucket is so much larger that it does have more mass, but the atoms in there are more spread out. Whereas if we look at, say, this gold ring, and we were to look at the atoms in there, and sorry, ignore my not very good drawing, well, the atoms in that gold ring would be very, 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 very close together. So given a certain amount of volume or space, there's going to be a ton of atoms in there, therefore making this gold ring much more dense than the bucket of water, even though the bucket of water has a larger mass. So now if we look at this equation for density, we will see that density is equal to an object's mass divided by its volume. And I can write density in here as well. One way I've had students in the past tell me they remember this equation is they say that D is equal to broken heart. So you can kind of picture the M and V as being a broken heart. I don't know, whatever works for you. But how much matter or mass is in a certain volume is the definition of density. But it can be a little hard to really understand what that means. So let's look at some examples. So now let's focus on what happens when we change one variable. So let's see how mass, volume, and density all relate to each other. In order to do this, I actually like to picture an analogy in my head. So I like to picture it like a classroom with students. So here's my classroom, and my classroom size is going to be my volume. So I'm going to go through and I'm going to label volume as classroom. Mass is going to be like the number of students. And then density, I like to think about how packed the students are in the classroom. So the more packed they are in there, or the more crammed they are in there, equals higher density. And then the more spread out they are, spread out equals lower density. So, if I go through and I try this one, it says if mass increases and volume stays the same, then density. So let's pretend I have 10 students in my classroom. So now it says if my mass increases, okay, so I add more students in. So instead of 10 students, I now have like 18. And my volume stays the same, so my classroom stays the same size. Well, what happens to my density? Well, in this case, my students are now more packed in there. Because I didn't increase, I kept my classroom the same size, we put more students in there. So therefore, my students are more packed in there, which means I have a higher density, or we could say that my density increases. Okay, so let's try a second one. If volume increases and mass stays the same, then what happens to density? So I'm going to draw the classroom again, and we're going to put our 10 students in there. And now it says if volume increases, so therefore, we're going to knock out this wall. We're going to take over another classroom, and we're going to make our classroom twice as big. But the mass stays the same, so therefore we're not adding more students. Well, what are the students going to do? Some of these students are going to take off and they're going to run over into the other part of the classroom. So now, are the students more packed or more spread out? Well, they're more spread out, and since they're more spread out, they have a lower density. So therefore, our density is going to decrease. At this point, I would like you to please pause the video and try the next two examples on your own. Alright, now that you have tried those two on your own, let's go through and look at them. So number 3 says, if mass increases and density stays the same, then what happens to volume? Okay, so we're going to draw our classroom again. And we're going to add in our 10 students. And says if my mass increases, but I want density to stay the same, so I don't want students to be more packed, I don't want them to be more spread out, I want to keep them the same. Well, if my mass increases, that means I have to add students in. And if I start adding students in like this, you'll notice that they're getting more packed in there. So what we'd actually have to do is, again, knock out the wall, if you will, give them more room, and now students would be able to remain equally spread out like they were before. So therefore, if my mass increases and density stays the same, in order for that to happen, we would have to extend our classroom or we'd have to increase our volume. So therefore, our volume would increase. Sorry, it's really bad handwriting. And we're going to use that analogy one last time here for question number 4. So I'm going to draw my classroom and we're going to put our 10 students in there. And now it says if density decreases, meaning the students are more spread out, and volume stays the same, so our classroom has to remain the same size, then what happens to mass? Well, the only way for me to spread the students out more while keeping the classroom the same size would be to actually remove students. And now you can see, as we remove students, they're now more spread out, so therefore the density has decreased while volume stayed the same. So therefore, if we lost students, the mass would have to decrease as well. Another thing to keep in mind with density is that water has a density of what we call 1 gram per milliliter. So again, remember how density equaled mass divided by volume? You'll notice units always follow through as well. So mass has units of grams, volume, we use units of milliliters. Well, guess what? That is where we get our grams per milliliter. So your units should always tell you what it is you're working with. Well, anything that has a density less than 1 gram per milliliter, so anything that has a density less than water, is going to float. So like when you saw that Diet Coke can at the beginning of the slides, well, it has a density less than 1. And anything with a density greater than 1 will sink. So like that regular Coke that sits at the bottom of water, that has a density greater than 1 gram per milliliter.